Okay, and so what we're going to look at tonight is linear regression, which is kind of the first thing everybody does when they're doing a little bit of machine learning. So it's one of the simpler machine learning algorithms, but it's usually a very good place to start. So firstly, we maybe need to define what we mean by regression in case you haven't come across the term before. So this is where we try to zone in on continuous values rather than trying to predict a class or a category. So rather than saying that this is going to be category A or category B or something, we're trying to actually zone in on a value like 3.57 or something like that. So in other words, something that has a continuous set of values, and we want to try and predict what that value is. It's much more difficult to get this right, and in fact, we generally find with a lot of machine learning algorithms that they perform a little bit better when it comes to determining whether something is in one class or another than they do in terms of regression. But nonetheless, there are certain problems that just lend themselves to being a regression type problem, and for that reason, we have to know something about them and try and solve them as problems. So, for example, if we're trying to predict the distance to a pedestrian, if we're thinking about our autonomous vehicles applications, trying to predict the distance to a pedestrian or maybe the distance to another car from the ego vehicle, so from the vehicle that we're in, this would be a regression problem because we're trying to say, well, how many meters, how many feet, or how many centimeters they are away from us. On the other hand, if we were trying to predict whether something was a pedestrian or a cyclist or a car, in that particular case, we would be trying to classify or categorize them. That would not be a regression problem. So where we're trying to determine a number, that's generally a regression problem. Okay. So I have my little, you'll see me looking off to the side here every now and then. It's because I have another machine here, which I'm monitoring it just to make sure that everything is still running. Okay. So I've seen a few more people have come in there in the meantime. Just a reminder that I do put these up on YouTube. So if you don't want your name appearing, make sure to log out and log back in again under an alias. Okay. So linear regression is the particular thing that we're going to look at tonight, although we'll mention a few other things around it. And where we're talking about linear regression, we're trying to fit a straight line. So that's the linear part of it. So we're trying to fit a correct straight line that matches the data that we're dealing with. So think carefully about why we might want to do this. Why would we want to fit a straight line to data that wasn't necessarily all on a straight line? And it's maybe not what you think of as machine learning, but remember, when it comes to machine learning, what we're trying to do is we're trying to learn a model of something so that we can then predict new values. So we have some data, and we want to predict values where we don't have data. So when I say we have data, what we normally have is we have information and we know the result of that information. Okay, so we know what type it is. But later on, we're going to have new piece of information coming in and we want to predict a new value. Okay, so we want to do something like that. And for that, we need to learn a model. So this is what the fitting of a straight line, the whole point of it is that we want that to be our model, and therefore when we come up with a new set of input information, we want to be able to predict an output set of information from that. And when I say predict, by the way, all I really mean is that we're going to put our information into our model and see what number comes out, and that is our prediction. So we need a model that we will train on the data so that the model can then predict new data. But what should our model look like and how complex should it be? Okay, and that's a much more difficult problem actually than any of the individual models that we're going to do. So in this particular case, we're going to deal with, as I say, linear regression. That's a particular type of model. And what we're assuming is that models our data well. But that may not be the case. It may not be an appropriate way to model our data. So linear regression is probably the simplest of the models that we can possibly deal with. We're assuming that the data lies on or close to a straight line. Now, if that isn't correct, then we can train our model all we want. We're not going to get a good model of our data because we've assumed it's too simplistic. So this could be a straight line in an n-dimensional space, but a straight line nonetheless. So what we're going to deal with here is we're going to deal with a one-dimensional space, and that makes it very easy for us to be able to graph it, draw it, and understand it. But the truth is that this could be a much higher dimensional space. We could have 10 dimensions or 30 dimensions or something like that. And once you go drawing more than 2 or 3 dimensions, it becomes very, very difficult to draw, and then it becomes very difficult to visualize what's happening. But you can think of a three-dimensional space relatively easy. You've got your x coordinate and your y coordinate and your z coordinate there, and you can have a straight line passing through that space, no problem. It doesn't have to be along any of those lines or anything like that. So if you have something like that, that's perfectly fine. But once you get to beyond that, 4 dimensions, 5 dimensions, and 6 dimensions, and so on, it becomes much harder to visualize what that is, and your straight line has to go along all of those dimensions there. Okay, so from that point of view, we're going to start with the simplistic one and look at it that way. But just do be aware that we can have, kind of these higher dimensional straight lines that do effectively the same job. We're still trying to find a kind of a route through the data that seems to match what we have. So I'm going to start with what seems like a really trivial example, which is how to cook a turkey. And the reason I'm using such a simple example is that this is one that you can almost explain to anybody, whether they're from an engineering background or not. And particularly if you're from an Irish background and you celebrate Christmas in some way or other, you'll have come across this example in some way. So for those who are not from an Irish background, at Christmas, the meal of choice tends to be a turkey dinner that they cook and eat on Christmas Day, and it's actually not particularly popular the rest of the year round. So what tends to happen is we go cooking this turkey on Christmas Day, and we have to try and remember a set of rules by which we cook this, because we don't cook it every other or regularly during the year. We need to kind of set of rules that we remember quite easily. So there's a particular rule of thumb that goes with this, and I'm sure if any of you are from Ireland, you've probably heard this before, which is that you into a preheated oven, you put in your turkey, and this obviously should be a defrosted turkey. When this was originally developed, I'm sure there were no refrigeration. And the idea is you put it in and you say 20 minutes per pound. So we're using imperial here rather than the metric system. So 20 minutes per pound plus 20 minutes. That's how long you should cook it for. And I think the temperatures are something like 180 degrees or something like that. I've forgotten what the exact temperature the oven is supposed to be at. But the question really about this is, where did this idea come from? Is it correct? Okay, so is this a good rule of thumb to follow? And what could happen if it goes wrong? Now let's start with that. What could happen if it goes wrong? Because this is one of the things that when it comes to something like a turkey, if we cook it wrong, it's either not going to taste nice or, well, what's the other problem? If it doesn't taste nice is one thing. What's the other problem? Yeah, salmonella. Okay, so we could end ourselves up in hospital by giving ourselves, there's going to be bugs and so on, bacteria in the turkey itself. That's perfectly fine as long as we cook it for long enough. It will kill off that bacteria, and that's one of the principal reasons that we cook food. The other is that it kind of starts the process of digestion, so it does some of the hard work for our stomach. But the principal reason is actually to kill off the bacteria that would be in it. So this is actually a reasonably good example to kind of ease ourselves in, because if you think about things like autonomous vehicles, we often think that if we just come up with a very good model, that'll be great. But if our model is not correct, what happens when it goes wrong, in other words, when it does exactly what it thinks it should do, but that doesn't actually match reality, is that we can have accidents occur. So on the one side, it might just be overly cautious, and on the other side, it could cause an accident. And that's why it's important that you understand that these models, even the simplest of models like this one, you can't be a slave to them. You have to actually think about whether they are appropriate to the problem that you're actually dealing with. So this particular example, where exactly did it come from? I don't know. How old is it? I don't know. It certainly probably predates the metric system. But the thing is that what most people don't realize is that this is just a very simple linear model for cooking a turkey. And what I mean by that is, if we draw, so we've only one dimension here. Okay, I know this looks like we've two dimensions, but we've one dimension in and one dimension out. Okay, so our dimension in is going to be the size of the turkey. Okay, size of the turkey, and our dimension out is cooking time. And what this is saying is that we need to have a straight line here. Okay. So this is a linear model. That hasn't drawn that very straight for some reason. I'll do it again. Okay, so a straight line there, and we have two things. We have this where it crosses the where it crosses the y-axis here, and we also have the slope of it here, okay? And where it crosses the line here, this part here, that is the 20 minutes, okay? So 20 minutes. And the slope of it here is actually 20 minutes per pound. So the size is given in pounds. If it was given in kilos, we'd have some other value, but the slope would effectively be the same. So that's the slope here, which is 20 minutes minutes per pound. Okay. Now this has some interesting parts to it, because when we think about whether this is correct, some unusual parts to this is that if we have no turkey at all, okay, so let's say you just have no turkey, this model still says that you should cook that 0 turkey for 20 minutes, and that clearly sounds like there's something wrong with that idea. Okay, so clearly this is not a perfect model, but then again, how often do you come across a situation where somebody wants to cook a 0 turkey? It doesn't really come about. And what will normally happen is that most of our turkeys will exist within some range of values, and really the question is whether this is a good model then within those range of values, because these ones down here probably don't happen very often. Okay. So this is a linear model, which is likely based on a linear regression analysis of different weights of turkeys. And it's the mathematical model is, and of course you can write this in loads of different ways. I've written it this simply because it matches the names that we're dealing with. Okay, but you know, so in other words, time is what's coming out. What have we coming in? This is the same as saying y equals mx plus c, which is what some of you might remember as your one for a straight line. The other one is ax plus b, is another popular one that that maths teachers use. I've put mw here because of the weight. The w is the weight, and c being the intersection where we cross. Okay, and I'm going to change those later when it comes to doing more you know, more general sort of ones. So don't get wedded to those particular variables, because actually I'm going to be using the m for something else later and the w for something else later as well. So this is where t is the estimated cooking time in minutes, w is the weight in pounds, m is the slope of the line, which is 20 in this case, and c is the y-intercept, also 20 in this case. Now this guy, I went looking this up obviously when I went to write this lecture, and this guy Panofsky, I hope I've done a reasonable job on pronouncing his name. He disagreed with this model, and he came up with the following model. And again, time is what's coming out. This is our weight. He says take that to the power of 2/3 and divide it by 1.5. Okay, and he says this is what you should do. Now, what's the problem, do you think, between this one and this one when it comes to its use in the real world? Okay, because if he says this is more correct, and maybe he's right, what's the problem with this one? Can anyone think of any problems when it comes to cooking turkeys Christmas morning? Yeah, so the whole thing is that first one there is very, very simplistic. Almost anyone can follow it. If you try to even word that w to the power of 2/3 divided by 1.5, for starters, is anyone going to be able to take anything to the power of 2/3 without grabbing a calculator? Probably not. Are they going to put it into the calculator correctly, given that many of the people that are going to attempt this have not done maths in years? Chances are probably not. Okay, now if there was some other system whereby they looked up a table or that would be fine, but in truth, we can see why the linear model is so useful. For humans, it's really easy to follow. For a computer, it's really easy to calculate. And that is the real benefit of something like a linear model, is its simplicity. Where some of these other models may well be more correct to what it's in the real world, but it's absolutely useless if it's not used, as you can see. So let's have a look at comparing the two models. First, notice that the linear model, you have to cook an imaginary turkey for 20 minutes, which of course doesn't happen with PF's one. Between £1 and £6, which is actually not that big of a turkey, it should be pointed out. The models are very similar. So we've a section here where the models are very, very similar. Okay, and then they begin to diverge. And there's actually a 90-minute difference here between those two. And 90 minutes, you know, is that big or small? Well, in terms of the idea that this one is cooked for 250 minutes and this is for 340, 90 is quite a considerable amount of time in the difference between the two. And that's for maybe a 16-pound turkey, which is, I think, probably quite a sizable one. But to be honest, I haven't gone and looked at it since I originally wrote these notes, so I'm not entirely certain if that's how big a family that would feed. Okay, but it's probably a reasonably big one. So, few questions on this. Let's say we decide to go with PFS1 or we decide to go with the linear model. Which do you think is safer? Okay, which can we guarantee is less likely to give you salmonella? Yeah. Okay, so the first one here, and that's because you're cooking it for longer. So there's far more chance there that you're less likely to cause harm by doing this. Okay, which tastes better? Again, that's going to be dependent on taste. But I think a lot of people, when you talk to them who are cooking the turkey, they will regularly say, "Oh, if you follow that rule of thumb, it ends up as a very dry turkey and it doesn't taste particularly nice." Okay, now, a lot of people said that about turkey anyway, so that doesn't really mean much. But it could be that their only experience of turkey is that they've all been overcooked. But certainly there is a major concern when it comes to Christmas time in Ireland that people will, on a large scale, give themselves food poisoning simply because they're not used to cooking this particular meal, and if they get it wrong, we want them to get it wrong on the side that means that it just won't taste particularly nice, rather than on the side that gives an entire family food poisoning, because you would have the emergency services would literally be full of people in a bad state, and on a day of the year where you really don't want that, because you've probably got less staff and so on to deal with it. So you can see why models like this, and particularly back when this model would have originally been developed, the hospital system would have been nowhere near as good as it is now, and therefore it was vitally important that people kept themselves safe. Obviously, the best idea, and there are some other tricks I think people have, where if you twist the leg of the turkey or something and it comes off easily, but you can only test that once. Really the best way is to test it with a meat thermometer and make sure that it's up above a particular threshold. I'm not going to state what that threshold is because I've forgotten off the top of my head. It's either 64 or 74, somewhere around that in terms of Celsius. But you should check that out rather than believing me. I know how to do linear algebra or these linear regression models, but I'm not particularly good at cooking a turkey, so don't take my advice when it comes to that. So use a meat thermometer would be obviously the best way to do it. So the question is then, how did they come up with this in the first place? So with the above example, we see the result of a linear model, but how was it arrived at? Okay, so to do that, we have to collect some data and fit the best line to it. So in the above case, this would mean cooking many turkeys of various weights and cooking them all using some calibrated method. Okay, so we'd have to calibrate it to something else. That might be that you have a meat thermometer, but likely when this was originally come up with, meat thermometers were not in existence. They would have had thermometers, all right, but it would have been much harder to be able to push that into the centre of the turkey. So much more likely that an expert cook would have been used with experience to cook many of these by some scientific method. Either that, or just many people over a period of time wrote down how long to spend, and when they went and looked at all the data, they were able to see that this was a general trend. It's also possible that this is just something that kind of organically happened, where people kind of zeroed in on this. They probably started with lots of different numbers at different times in saying how to do it, and then people just gradually began to see that the wisdom of the crowd said that it should be somewhere in this range. And of course, that would be very dependent on the size of the turkeys and so on that people would have been making. Okay, now let's look at some data, and I need to be straight up with you here. The data that I've shown here for experimental cooking times. Firstly, I didn't go and cook a load of turkeys myself or anything like that. Secondly, this is not real data. What I've done is I've faked this data simply for to be able to show you an example of it. Okay, so this is not real data, but it does show you the sort of way that real data might actually be collected and how many we might have, and therefore what you might want to do in order to make a model from it. So given the data to the left, I don't know why I've said to the left, it's on the right clearly. So we'll ignore that, pretend that doesn't exist. If you had a 9-pound turkey, how long should you cook it for? So what we would do in this particular case is we would come up here at 9 in a straight line, and we'd see where we'd meet. Now, as you can see here, there's kind of a few here that are candidates, right? We've one there, use smaller. So we've one there, we've one there, and we've one there as data points. But you can see that there's quite a bit of difference between those data points there. So if we look at that there, this would suggest just over 150 minutes. And if we look at this here, that would suggest maybe 100 and what? It'd be about 180, maybe 185. And this would be maybe about 190. Okay, so clearly there's quite a difference between those. So which of those would we pick? So you can see that the problem is that what we're doing then is that we're trying to say how long we should cook a 9-pound turkey for by only looking at 3 pieces of data. So 3 turkeys that were around about that. And as you can see, there's a considerable difference between the different ones that we did. Okay. So instead what they do is we'll just delete that. Instead what they do is they try and come up with a straight line. Something like that. And they say, okay, this is going to be our straight line looking at all the data. And we can see that it's got a crossing point here. I don't think my crossing point is exactly at 20 because I probably haven't drawn it perfectly. And secondly, then what we can do is that this straight line is going to be our model. And going with that, what we would do is we would hit this particular point on the graph. We'd bring our line over there and we'd say, okay, you're going to cook it for maybe about 160 minutes. Okay, so we make our model or our straight line here, a fairly simple model in this case, from the data that's there. And then from that model, when we have a new turkey that we want to cook, we use that model to make our decision. And clearly then this model should be what they come up with previously, which is the 20 minutes per pound. So 20 by the weight plus 20 minutes. Okay. Which is, we see, we have written here, T equals MW plus C. So my question for you now is, coming up with this model here that we're going to come up with, would you refer to this as a supervised, which you can just type in as an S, or an unsupervised learning task? So a U for unsupervised or an S for supervised. Which do you think we're doing here? Okay, I'm glad to see that you've all come up with the correct answer. So this is supervised. Why is it supervised? Well, we have data and we know the answer. So in other words, we have turkeys of all these sizes. We've cooked them and we've said that this is how long they should have been cooked for. So what we're assuming when we've got this data is that those points there, each one of those turkeys was cooked correctly. Why would we end up with all this variance that's in there? Well, for all sorts of reasons. You can imagine that different turkeys will be made up of different constituents, whether they were, whether some of the weight came from more bone or from more meat or whatever it might be. So there's lots of variables in there. There's obviously variables to do with our cooking. Was our cooker entirely up to heat? When we put it in there, how much thermal mass is in the cooker and all sorts of things. So there's quite a lot that can cause variance within the system. Because turkeys are not going to be particularly uniform. So that's why we see all that variance. But what we're assuming is that each one of these blue dots is an example of where somebody has cooked it and got an exact answer out from that. So therefore, we have supervised data that we're going to use in order to come up with our model. Once we've come up with our model, we can then try another example, another input into it. So if we assume a linear model, what are the parameters that we need to learn? So that's my next question. Assuming that I've used this model and I've called my variables what of these 4 letters do I have to learn in order to make my straight line? Okay, so which one of those letters do I have to learn? Okay, so we've got 2 answers so far. Anyone else? Okay, so we have Blohin is coming in with M. So we definitely have to learn M. That's certainly true. But as it happens, we're going to have to learn C as well. We don't learn W because W is the weight of the turkey. So maybe I should have gone back through what each of the letters were before I asked the question. So W is the weight of the turkey. So if we get a new turkey, we will know the weight of it. So we don't need to, that's not part of our model. What happens is that when we come in with a particular weight, we tell the model we've got this weight and it calculates what the time is going to be. So therefore, to calculate the time, it needs to know it needs to learn what the appropriate slope should be for cooking a turkey and what the appropriate crossing point of the y-axis should be. So what the minimum time should be for cooking a turkey. Okay, so it's gonna learn both of those, or that's what we would have to do in order to learn what this model would be. So what a training set for this might look like is that we would have lots of turkeys that we knew the weight of beforehand. Okay, that's fine. And we've gone and cooked them and we know how long it took to cook them. Okay, so we have each one of those sets. And I think in this particular case, I came up with 83 of them. Okay, I've made a little note here, by the way. I'm using capital M here for the number of samples, but later on I'm going to switch to using a lowercase m. Simply because it fits in with what we're doing later. We're using the capital M because we've already used the lowercase m in our function here. Okay, but we won't be doing that in the long run. That's just in this particular example, and it's because m is often related to slope. So W is our input variable or feature. T is our output and can be considered our regression target that we will use to train the model. We need to learn M and C, and we will also use the notation, the capital M, for the numbering of training samples. So M is equal to 83 in this case. So in each case, what we're doing is we give a kind of what we'll call a tuple here. This would sometimes be called a tuple. So two pieces of information, because the reason we call it a tuple is that while they're both floating point numbers in this particular case, that might not be the case. It could be something else. So the two pieces of information that go together, and what basically happens is the weight and the cooking time goes together, and this is our training data. So what we normally do in order to index through each one of these, okay, so let's say this is index 0, this is index 1, this is index 2, 3, 4, and so on up the way. We use the letter I to index those, but what we do is we put that up here looking like it's an exponent. That's why we put it in brackets, to kind of give you the impression that we're not actually taking it to the power there. That's just a way of indexing it. Now you might say, well, why not put the index down here? And the reason is that normally the indexing down there is for something else, and we're going to come across that later. Okay, so that's the reason for that. It's so that we can try and not get mixed up in the different things. So one training example would normally have a particular value there and a particular value here. Okay. So this is where I'm going to change over to new variable names, simply because we want to make this a little bit more general. But what you're going to see is that there is no real set in stone variable names that you use for these things. Why the first is P? Vin is asking me. Sorry, I'm not sure what you mean by P. Maybe you might tell me where's the P there. I'm not. Oh, 0. Okay, why is the first 0? Why do we start with 0? This tends to be. So you're asking me why is that one 0? This is a convention. Anybody that comes from electronic engineering generally starts indexing at 0, and people who start from a mathematical point of view generally start their indexing at 1. It's simply down to that. So as long as you're consistent, there's no real problem. Okay, but that's all that is. It's nothing too much to worry. When I say there's nothing too much to worry about, it's actually not a trivial problem, because it often in programming leads to out by 1 errors. But most programming languages in that would kind of assume that you're starting at 0 as well, like particularly the C programming language and so on. Okay, so as I say, I'm going to generalize because there's no particular convention that is used. So we're going to generalize this a bit. So you'll notice on the previous slides that we use variable names that either match the problem or that are used regularly in mathematics, so such as the one for straight line. However, we'll not always be dealing with linear models, so we're going to use notation that can be scaled up to larger models. There isn't a set notation, so where possible, I use whatever is used in scikit-learn. So this is a very, very good resource that you're going to be making lots of use of, because it's a library that we can use with Python to do a lot of the machine learning that we're going to do. And indeed, even from tonight, I want you to start getting that up and running in a Python programming environment, and start trying to use it maybe to do something like a linear regression model. There will be assignments coming up in a few weeks' time. There'll be big assignments, and that is not the time that you want to be fiddling about with how to learn Python and how to use these libraries. You should be fiddling about with that now, playing about with it, and getting it to work. So you should kind of start that from tonight or tomorrow. So we'll use either capital W or small w. I tend to use small w to represent the parameters or the weights that we're going to train. And we will most often use y as our output and x as our input. Okay, but you'll see that can confuse the issue as well later, because it really depends if we have more than one type of input, which we're going to see two different functions later on, where this can cause some confusion. So again, I'm going to let that confusion happen, and then we're going to correct it so that you see what can happen when we do it. So our above equation will now be something like y equals w0. So again, you can see I've indexed here w0 x plus w1. Now you'll notice that I've put the index down the bottom this time rather than up the top, and that's what I was referring to back here when I said that these are indexing each of our samples, whereas what's happening here is that we're indexing something that's part of a vector. Okay, so our weight has multiple parts to it, so multiple dimensions to it. So this is a two-dimensional. The weight here is the things that we're going to learn are two-dimensional. If you remember last time, we called this one M and we called this one C. Now I'm just calling them W0 and W1 as the two weights or parameters that we're going to have to learn, and I want to be able to tell them apart, so I'm going indexing them down there. The important point is that for each of our samples, there's going to be a set of those for each in each case. Okay, or a set of those that we're going to learn in each case. Okay, I'm not saying that correctly. How better to put that? So in other words, in each case, we're going to be trying to learn just one of these for all of our different samples. Okay, but the point is that it's not indexed. It's not indexing of samples, and that's why it's down in the lower, in the subscript part rather than in the superscript part. That'll maybe become a bit more obvious as you see more examples. Okay. So choosing a model. So as we can see from the previous slide, there are two learnable parameters, but to make things even easier to begin with, we'll use just one of them and then scale up from there. So we'll use y equals w0 of x. So what I've done is now I've lost the plus c off the end, okay, or the w1. I've lost that off the end. Going to make it very simple. And what we're saying is that for our model here, we are going to make sure that our straight line has to pass through our origin. Okay, so it might be something. It might be this one, or it might be this one, but the point is it has to pass through the origin. It's not allowed pass through at some y-intercept there. Okay, so we're keeping this model very, very simple, simply so that we only have one parameter to learn. So strictly speaking, this is what's called a linear model, and the one that we saw previously that had the extra one, that's often called an affine model. But the problem is the affine model is so regularly called a linear model that it tends up to end up just being confusing between the two. For something to be strictly linear, it must pass through the origin, and that's the reason why this one is strictly called a linear model and the other one's called an affine model. This suits our purposes right now. After all, a zero turkey should take zero time to cook, as we agreed. But is this the right model, or is it just the simplest model? And I think we agree it's unlikely that that cooking a turkey is actually a linear problem at all. Okay. But nonetheless, this is a nice simple one to use, and we think that people might use it then if we did make it. So how do we know if we have a bad model or just bad parameters? Because you could have come up with the right model and train it badly, and then you end up with the wrong parameters. So you have a linear model, but instead of 20 minutes per pound plus 20 minutes, you've got 10 minutes per pound plus 50 minutes or something like that, and then that's the wrong model. Okay, so how do you know between a bad model and bad parameters? Well, this all depends on something called a loss function. Okay, so this is also known as the cost function. So from that, we need to be able to measure how well we're doing. So this measures the difference between what the model predicts the value should be and what the training sample actually was. Okay. So for example, if we look at our straight line model back the way here, what this will do in each case is it'll measure the distance from each sample down to our line, and it'll calculate that as a loss. Okay, so the further it is away, the more of a loss we get. Okay. Where are we? I think that's where we were. So this measures the difference between what the model predicts the value should be and what the training sample actually was. You may think this is straightforward, but actually there are lots of ways of measuring the loss as well, and choosing the wrong one can be like choosing the wrong type of model. Okay, so we really only just moved the problem on a bit, really, rather than solving the problem. A typical example, though, is the mean squared error, and this is one we use a lot, so it's usually a good place to start, unless you find some other reason to do it. So here, small m now, I've moved to using small m as the number of samples, and what I've said is my loss is going to be calculated by the following: 1 over 2m times the sum of the following. This here is our model. Remember, we have a very simple model with just one parameter w0 and each sample then xi going into that. Okay. And what we're going to do is, and actually I've gone and done the thing. The xi should really be up here. So I've gone and made the exact mistake that I shouldn't have made. So we'll put the I up there, and the I up there is what these should be. Okay, rather than down there. I'll fix those in the slides later. So the idea here is that what we do is we operate our model x by w0, which is just going to figure out where we are on the thing, and we're going to subtract away from that the actual value that the sample suggests. So if we go back to our example, somebody cooked a turkey of a particular size, they got a particular answer here in terms of y. Our model then is going to predict what it should be, and we're going to subtract one from the other in order to determine whether to see what the difference is between those two things. Okay, and then we're going to square it. Okay, so we're going to square this rather than just using the value that we got. So there's two things here with this. Let's have a look at this model. I've removed the indexing here for the W in order to make it a little bit easier on ourselves. There's two things that are a bit strange here. Firstly, why are we bothering squaring it? So this is just one example of a loss function. We don't have to square it if we don't want to, but we probably would have to make sure that our numbering here doesn't end up with negative numbers. So we'd have to use something like getting the absolute value like that. So we say x I w minus y I. Okay, get the absolute value of it. The reason sometimes we use a squared version, well, is firstly that it's easier to optimize, and we'll explain why that might be in a while. And the second thing is that what it does is it says if you have a value that's a long way away, that should be much more extreme than a value that's quite close to our model. Okay, so it really penalizes heavily anything that the model is far away from. Okay, but the main reason is that this is an easier one to optimize than most. So the second question then is, why are we dividing by 2m? Why are we dividing? Because we obviously want to get the average loss here of all our different of all our samples. Why are we dividing by 2m rather than just m? And this, it turns out, is just for mathematical convenience. Later on, that in some other operation that we're going to do, I'm not going to tell you what it is because I'm going to ask it as a question, but later on that will get cancelled out in some other operation we're going to do. So that's the reason for that. And it turns out that it doesn't really matter if I minimize 1 over m or 1 over 2m. Yes, we'll get a different value, but they'll both occur at the same place. So it won't affect where our minimized point is. So remember, we want to minimize our loss here. We want this to be the smallest. We want to end up with a model that has the smallest loss. And therefore, this is something that we're going to want to minimize. As long as we end up with the same model, whether we used 1 over 2m or 1 over m, then it doesn't really matter which we use. So it's purely as a mathematical convenience. We're going to see in a moment what the convenience is. So how do we train the parameters? So the idea is to change the parameter w until this loss function is at its minimum, ideally 0. Okay, so that every point lies perfectly on the line. As we see, that's unrealistic in most cases, but it may be possible. So how do we find the minimum of a function? So while you're thinking of the answer to that, because I want you to answer that for me, how do we find the minimum of a function? I'm going to draw some sort of function here. Okay, so we've got let's just x as our input and f of x as our function here. So how do we find the minimum? Okay, so we want to find this point here. So Olivia has given us the answer, and what she's basically saying is you're going to get the derivative of it. You're going to get the you're going to differentiate it. And if you remember differentiation, what that does is it finds the slope of the tangent to the curve. Vin has mentioned the slope there. It finds the slope of the tangent to the curve. Now we could have a tangent at any given point along here, like there could be a tangent there, there could be a tangent here. But there's one particular tangent that's of interest to us, and it's the tangent where the slope of our tangent is 0. So if we can do a derivative of the entire function and find where the slope is 0, then what we can do is we can figure out that that is the minimum of our function. Okay, so that's the idea. There are a few problems with it, one of which is that we actually also get a slope of 0 at our maximum point. So you may, depending on the type of function, have to figure out whether it's a maximum or a minimum you found, because there's no good finding a maximum. That's worse than anything. So that's one of the things to be aware of when it comes to these things. So the standard method you may be familiar with is to take the derivative of the function with respect to the parameter of interest and set it to 0. Then solve for the parameter you are interested in so that you figure out exactly where along that parameter space that happens. So what we want to know is this point here. That's what we want to know. I'll put it as an X maybe. That's what we want to figure out. Where does that happen? And then you solve for the parameter you're interested in, with some caveats, obviously the caveats being that you may have found the maximum as well. So what we've done here is we've gotten the derivative of that function that we had a while ago. Let's go back and look at that. When you get the derivative of, this is a function of a function, and we're getting the derivative with respect to w. So the first thing is we've got the entirety that's in there, and it's squared. So what that will end up being is 2 times x, I'll put my I up there, do it properly this time, xi, w minus yi, like that. Okay, so it's 2 times that. What's going to happen to 2? It's going to cancel out with that 2, and that's where our mathematical convenience comes in. The next thing is we have to get the derivative of what's inside the function, and there's only one part of this that's relevant here, because we're going to get the derivative with respect to w. This has no w part in it, and therefore it's the same as having a constant, but this one does, and therefore the result is going to be xi. So our total then is going to be, as we have it written here, which is xi. Again, I'll fix those later and put the i's up in the superscript. Multiply by xi, and we get the sum of all of those, and we set that equal to 0. And what we need to do is try and figure out what value of w that works out for. Okay, so that's how that would be done. Don't worry too much about the sum, because effectively when it comes to derivatives, a sum, you can just do each one of them separately, so that doesn't really affect things at all. Be careful not to get confused here and try to find the minimum of the model equation. So if you remember, the original model equation was y equals w wxi, or xiw, whichever way you want to put it, plus nothing in this case. We were just doing it, that's all we were doing in this case. We don't want to find the minimum of this function, because that's a straight line, so you're going to be going a long time before you find the minimum of that function. It'll never be a derivative of 0 unless it's a straight line across the way. That will do you no good. What we want to do is we want to find the derivative of our loss function, and it's with respect to our parameters. That way then we can find out what our appropriate model should be. Okay. So try and remember that, and that will come up again and again. So what does the loss function look like? So it won't take too long on this, but it's a squared function, and because of that we call it a quadratic. And what happens then is, in terms of our loss function, in terms of changing w here, which is our input, and this is our loss function there, we're going to get something that looks like this. Okay, which is like a kind of a bowl shape, except that it's only in one dimension here, but in two dimensions you can kind of you'll end up with a bowl, or you can go into higher dimensions again. And the idea is that there's some point here at the bottom of this, okay? So you've come across these quadratics before. You would have done them in secondary school and tried to find the roots of them and so on. This would have imaginary roots because this is our 0 point. So this never, in our particular example that I've done here, I've shown it that it never gets down to a loss of 0. That's perfectly fine. What we will want to find out is what is our minimum loss. So what's the lowest that can get, and what is the tangent of that is going to be 0 at that particular point, and we want to find out the w, or the weight that's best for that. And what that then means is we can then put that into our model, which is y equals w times x, and that will calculate. So if we put in a new value of x, we use the w that we calculated for the minimum, and that will give us the correct value of y when it comes out. Okay, so that's how the whole thing, we close the loop on it. Okay, so the above method that we mentioned, which is get the derivative, set it to 0 and so on, that's great, okay, and it's definitely the way to go if we're dealing with small numbers of parameters or features, but we only have we only have one of these in each case. But where we get into tens of thousands of parameters, so you've basically not got just a single dimension, you've got thousands of dimensions. It turns out to be quite inefficient to try and do this, because you've got to calculate, you've got to do a lot of matrix inversion and things like that in order to try and determine where the appropriate point is. So another method is called gradient descent. And gradient descent is a first order method in that it uses first order derivatives. There are other ones that use second order derivatives, Newton methods, where they're looking for zero crossings. We're not going to mention those at the moment. But this is a first order method, uses first derivatives, and it aims to find a minimum of the function. Now, just before the lecture, I was looking through these in the last hour, and I was deciding that I was going to change this function, which I have changed them in the notes, but I've actually left them the way they are for the moment. There's nothing incorrect here, but the problem is that this is a very general function, and this is where I said we're going to have a little bit of confusion between this and the function I showed previously. But basically, this is what happens in gradient descent. We want to update some value called x, and at time equal to t plus 1, in other words, our next timestamp, we want to take the previous value of x and we want to subtract from that some value. And what we're going to do is we're going to say, we're going to use what's called a learning rate, alpha, and we're going to have some function here, f of x of t at the previous time. Okay, so this symbol here, which is I think it's Greek, though it could be Latin either, I'm not sure, nabla, that's not too important. What we use it for here is gradient. And by gradient, I basically mean the first derivative of the function. Okay, so you can think of it as dy dx or whatever. So what we're basically saying is we want to find the gradient of the function at this particular place. Okay, we want to multiply that by some learning rate, and we want to subtract that from our current value to find our new value. Now the problem with this is that I want you to think about what is f in our case. And what I mean by what is our function, so what's our function in our case? And the question that I'm asking you here is, am I dealing with the original function, the y equals w by x, or am I dealing with the loss function, L, where we had 1 over 2m, and the sum, and so on, so we would the w, wx minus y. Are we dealing with that one? So are we dealing with the loss, or are we dealing with the original function here? So there was a break in the recording there. So what I'm just going to do is just remind ourselves of what we were covering here. So we were talking here about gradient descent, and we were showing the algorithm to do it. But I asked the question, which function are we referring to here? Was it the original model function, or was it the loss function? And Those that answered correctly said it was the loss, but that's a bit confusing, and the reason for that is that because of the way that I wrote it here. So when we be dealing with the loss and using the variable names that we had up until now, we should really say W equal WT plus 1. So the next weight value will be equal to the previous weight value minus alpha times the gradient. So alpha times the gradient of the loss function. We could write it as L if we want, of W at timestamp T. So the idea here is that our weight function, our weight here, W, is going to change with each step of this algorithm. That's the idea. Okay, so this is how we're going to update the weight. So rather than going in one fell swoop like we did here and figure out what W is, instead we're going to try and get there in steps. And what I might do is I might just actually grab this for the next slide here. I have no paste. Where are we going? Oh, my pencil isn't working for some reason. We'll have to draw it again. Okay, so we've got some function here, and it goes something like that. And alpha is the learning rate. I'm going to explain that now in a bit more detail here, Vin, so it'll become a little clearer. So we want to find this. I'll call this W star, as in it's the place where we want to get, right? And this is our weights. So let's say we begin somewhere else. We begin with some other value of our weight. Let's say we begin here. So what happens is that we want to make our way in steps down this direction. Now, how do we do that? Well, the first thing is that we're going to get, we're going to find out what's the gradient. In other words, what's the slope of the tangent to the curve at any given point. So that's the first thing. And then what we're going to do is we're going to move in the negative direction. So hence the minus here, because we don't want to move up the gradient, we want to move down the gradient. So depending on how big that gradient is, we're going to make a certain step in that direction. And that step size that we're going to make is called alpha. So the idea here is that we would step down this. At each step that we go, our gradient is going to change. And by the way, you can also change the alpha value as you go as well, but there's no real need in this particular simple case. And as you can see, we're going to step our way down. So we're going to step our way down here into the thing here as we go. Okay. And the hope is that we will stop just at the W, or we might overshoot a bit and so on and go on the way. However, if we use a big value of alpha, what we're going to do is we're going to make and I'll maybe just use a different color for the big value of alpha. We're going to make a huge step down in that direction, and that might be fine, except for the fact that the next step we might overshoot. Okay, and in that case then we make a big jump back, and we kind of hop about in here for quite some time, and we never get to the bottom of it. On the other hand, if we use an alpha that's too small, we're going to be forever getting down into where we're trying to find the thing. But basically what we want to do is we want to continue this algorithm bit by bit until that loss no longer goes down, and then we know we're usually at the minus point. Okay, hopefully that answers your question, Vin. You can see there's basically the length of those arrows as to what our alpha is. Okay, so alpha is called the learning rate. And so we added yet another parameter, we called it alpha. These are sometimes called hyperparameters to suggest that they are not learned but dictated by the user. What are the advantages and disadvantages of setting this to a high value? Well, we just mentioned that we might overshoot. What are the advantages and disadvantages of setting this to too low a value? It might take forever. Okay, so we can change the value during training, but what will happen if we don't in the above case? Will it settle at the bottom, or would it happen? What would happen if it started at the minimum? Is the second question. So the first question there is, would it settle at the bottom without changing the value of alpha? So let's say our alpha was slightly too big and it kept overshooting here. It didn't land perfectly on it. What would happen? Well, one of the things to be aware of is that the alpha is multiplied by the gradient. Okay. So, Vin, you're kind of answering the thing that, or asking the question that I'm just about to answer here, which is that if we leave alpha staying at the value it is, it's already being multiplied by the gradient, by the slope. And therefore, the idea is that as we get further down, those two numbers multiplied together will end up being a smaller value because the slope becomes smaller. And therefore, it will automatically, the jumps that we make are dependent on the slope and on the alpha value. So if we set it to a certain value, and that's working fine, the overall update will be smaller and smaller and smaller the closer that we get to W. That does also mean if you set a very low value that it will get slower and slower and slower and really slowly kind of never get to the point. So to be aware of that. So it should get there eventually, but it might take infinite time. But in any case, it should also get very, very close to it by doing that as well. Okay. So what would happen if we started at the minimum here? Well, if we started at the minimum, okay, let's go back to our formula here. So we'll maybe scrub off a bit here. If we went back to our formula here, and let's say that we started at the minimum point already. So this was already an optimal value. Our alpha would still have some value, but the gradient at that point would be 0. So therefore we would be basically subtracting 0 from it. And therefore this would not be a new value at that point. So that would work fine as well. So we wouldn't go heading off in some other direction if we were to start, if we just happen to start at the optimal value. So how does the gradient descent algorithm work? So what we do is we initialize the value of W to something random. It's often stated that we initialize it to 0, which will be fine. That would be setting the slope to 0 in this particular case. This can cause problems if used as a strategy for convolutional neural networks, as you are setting all filters to the same value. That will give a 0 output. We'll look more on that later, but the point is that in neural networks, actually, the bigger problem is that you're setting them all to the same value rather than necessarily setting them to 0. But the 0 can also be a bit of a problem as well because it can end you up not moving anywhere. But in this case, it would be fine to set W to 0 and you would effectively work from there. If we go right back to our example here, okay, imagine that we started with a slope of 0 along there. You can see that we have all of these different errors here. So it knows that this value is wrong and it would start to move it up in that general direction. Okay, so that would be fine. Okay, so we initialize it to something like 0. However, so it's fine in this case. You change W to reduce L using this formula here, which, as I said, we can put in the W into it. So instead we'll be putting in WT here in each case rather than XT. And you keep doing that until the result stops changing, which we call convergence. Okay. Now, there are a few problems with this. It doesn't happen in this particular case, but in other problems it may, in other types of models it may happen. And it's where we can have something like this. Okay, so what you can see is that as well as having maybe some, we have plenty of points here where we have a slope equal to 0. Some are maximum points, some are minimum points. Assuming that we know how to tell a minimum from a maximum, which we can do usually by just saying how things are moving around it, we still have more than one of these. We've got one there and we've got one there. So this would be what we would call a local minimum. And this is what we would call a global minimum, maybe for this particular function as being the smallest point. We prefer to find the global minimum, and in most cases it wouldn't really be acceptable to find a local minimum. But actually in our neural networks, all we'll ever find is local minimums, but we find that actually that's not too bad. They tend to be all somewhat close to global minimum, if not perfectly on it. Okay, so you can see here that what could happen is that our gradient descent algorithm, if it started here, could end up sitting in this one rather than hopping out of there and jumping down into there. Okay, and again there are you kind of have to look at that problem and try to determine if that's likely to happen, and then look at possible solutions to it. Okay, so some of the solutions are there's things called simulated annealing and things like that, where you try and pop them out of there. Maybe you try and use a large learning rate at first and then a smaller one, so the large learning rate tries to find the largest place first, and so on. Okay, so now we want to just maybe get an idea of linear regression with two variables, and the two variables that I mean here would be the two weights. So what we'd be referring to here is something like along the lines of y equal to w0, x0 plus w1, x1. Okay, so the two different parts of it. Now in the previous case, this was our C, and what our x1 would be nothing. There would be no part to that. Okay, but what you'll find is that we'll often do the following: is we'll set w to be a vector, which is w0 and w1, and what we'll do is we'll set x to be a vector, and even though x only has one part to it, we'll put x0, and we'll put a value just of 1 there, and that way then when we can do a w transpose x, multiply those together, and that will basically get the sum of those two together. Are you familiar with this sort of notation here? I know you've only just started linear algebra class. For some of you, I know some of you are well familiar with it from previous. Okay, so most of you are familiar with that. So that's what we can do in the case of two of those. And so basically what we change our loss function to is something along the lines of 1 over 2m. We do our sum as previously, so we go I equal to 0 up to m. We'll do our w transpose xi there like that, and then our our yi in each case. Okay, and what we'll do is we'll square that. So the idea is that we multiply the entire vector by the entire x in order to give our full, that would do our full model for us. That would do that sum, and then we sum up each sample as well. Okay, so it means that we can start to use linear algebra in a better way. Okay, what does the loss function look like if you've got two variables? Well, it looks like this. It's kind of a bowl shape. In this particular case, this bowl suggests that those are the same. In other words, there's the same loss in both of them, but that's not necessarily the case. So it won't necessarily be a perfect bowl shape. It might be asymmetrical. So we might end up with something along the lines of, so that one there, you can kind of think of it as having contour lines. Maybe use the circles here. Okay, having something like that. Okay, whereas you might have a situation whereby you have contour lines that look a bit more like this. So one has a bigger loss associated with it than the other, and it starts to go in this direction. Are you familiar with this idea of contour lines? Do you see how this matches back to something like this three-dimensional idea? Okay, so that's not new to you. So oftentimes what happens, if we can visualize it at all, which in many cases, if we go beyond 2 or 3 variables, we usually can't. But what we'll do is we'll show this idea of saying, okay, we have some mechanism whereby we're going to descend this down into the central point here, or down into the lowest point. Okay, same here, we might want to descend down into that there as well. So we kind of think of it that way, instead of just thinking it as going down into the center of a three-dimensional figure here. Now, one thing to mention here, I'm conscious of the time, but I'll get you out in the next 15 or 20 minutes, so I'll get you out for the next class. The simultaneous update, the main thing I want to mention here, I'm not necessarily going to go through it here, but we mentioned previously we had W0 and W1 as having 2 variables, and we could have many more variables than that. One important point is that when we update W0, we must update W1 at the same time, not wait for the result of the model after we've updated W0 and then update W1. That will go wrong on us. So you might think that you're updating W1 based on old information. So you must update W1 based on the information from the previous situation, rather than updating each one after each other. Okay, so you try and update them simultaneously. And all we mean by simultaneous is that we don't recalculate the loss until we've updated all of all of our variables, all of our parameters, all of our weights. Okay, so you update them all in one go, then you recalculate the loss, decide how much you're going to update all of your weights again, and do them like that. Don't update one weight and then recalculate your loss. That will lead you wrong. Okay, so that's what we mean by a simultaneous update. If we go beyond two features, this is where we really need to be able to use our linear algebra notation. So matrices and matrix and vectors. And I know some of you are only doing that module now, and some of you did it last year. So you need to know the following: how to add, subtract, multiply with matrices and vectors. Okay, so make sure you know that. You'll probably be learning that in the next few weeks anyway, but if you don't, make sure you go and learn it in the meantime. How to do a matrix inverse and how to do a matrix transpose. You need to be able to do both of those, and how to do a vector transpose is relatively simple. If you want a short targeted review of linear algebra for machine learning, you can see Andrew Ng's linear algebra review. Andrew Ng does a whole set of videos on linear algebra, or on machine learning, that are very useful, and you can click on that link and you can just go back to the beginning of the playlist. But there's a particular point around about where I am now as well, where he does a quick linear algebra review. I'm not going to do that because you've got a full module on it, but nonetheless, if you want to have a quick watch of those, maybe 4 or 5 videos in it, he does the main things that you're going to need to know. If you want a full set of lectures on linear algebra, I can't more highly recommend this guy, Gilbert Strang. MIT, he's an MIT lecturer, and this is a module from MIT called 1806, which is all on linear algebra. If you click on that, there's 35 recorded lectures of him going through linear algebra on a chalkboard. But he's a superb lecturer, and I think that would help you a lot with your linear algebra module as well. So that's definitely worth giving a look as well. So what happens if we go beyond two features here? So what features could we take into account for, let's say, if we were trying to determine the price of a car? So I'll give you a minute there maybe to just give me some suggestions. I have some written down here as well, but maybe just throw some suggestions at me as to what you reckon features we could take into account if we were trying to determine the price of a car. Okay, so I had written down the size of the engine, but Vin has said power, which is probably actually a better way of doing it, because you can have different size engines and not have the same amount of power. Mileage, Blohin is saying, I've that written down as well. The age of the car, certainly. I've also put down the miles per gallon, or kilometers. They have another way of doing that, isn't it? Liters per 100 kilometers or something like that. The number of doors, I think, affects the price of a car as well. And desirability would also affect it. Okay, so so I'll just actually quickly sketch those down. So engine size, or power. The reason is we're going to want to come back to these. MILAG, mileage. I don't know if that's spelled right, but I hope it is. I'm never sure whether to put in the E or not. MPG, so miles per gallon. Desirability. Number of doors, and the age of the car. Okay, so they're possible ones, and you can see there that what we're going to have to do is these are all input variables, so we're going to have weights to like a W0, a W1, a W2, W3, W4, and W5 to match those, to be multiplied by each of those. It does have an EU mileage, is it? So it should be like that. Okay, I knew it looked wrong, but it's that sort of thing that you're never entirely certain which the difference is. Okay, so we'll use n for the number of features here. So the way we would normally do this is we're going to look through each sample, xi, and it has the I of pi. Maybe put that in brackets. This is the ith training example, and the j then refers to each feature. So as you can see here, we might have j equal to 0 being, what do we have here? Engine size. So the idea here is that if we wrote down for a particular sample of a car, which we call x, let's call this x0, and we might have some of the following piece of information. We might have the size of the engine. It might be a 1.6 litre engine. Mileage, it might have 100,000 miles on it. Miles per gallon, let's say 30 miles to the gallon. And desirability, how would we do that? I'm gonna pick a number of 0.7 on terms of desirability, and basically decide that, let's say for example that a Ferrari is 1.0, and whatever your car of choice. It used to be the Lada, but lots of people like the Ladas now, so they're sought after. So whatever the boring car is, you might put that down at the zeros. Number of doors, well, let's say it has 4 doors, and the age of the car, let's say it's 4 years old. So you can see we've got this is an entire vector, and we're going to have to be able to multiply that by those. So basically this is j equal to 0, j equal to 1, and so on, but we're looking at a single sample here. And then you can see how we can very easily make up a full matrix of these things as well, okay, as we make all of the different ones. So how do we do multivariate linear regression? Well, what we do here is that we basically multiply our all the way through here, w0 by x0, w1 by x1, w2 by x2. I've gone, that should have been a 3 and a 4. I never spot these when I'm going through them the first time. So this is one way of looking at it, okay, and then you can see here that what I've got is some bias value here. And so this is kind of the suggestion that maybe no car, no matter what it is going to go below €300, and that might be because it just has scrappage value of that, okay, and then everything is built on top of that. And of course what we can do is we can just set x4 equal to 1, so that that's always included into our calculations, okay. So what do we do then? We do a W transpose X, so that's our little transpose symbol there, and then to calculate our loss, what we do is we do our function there, and we subtract it from that. We get the square of it again, and that's 1 over 2m again. So again, what we would do is we would get the derivative of this in order to or the gradient of this in order to work our way down through the system. So you can see it's done in pretty much exactly the same way. There's no real difference in terms of how it's done. It's just that we now move up to having a high dimensional vector. So gradient descent on multiple variables, what do? Well, we do the alpha and we multiply it by the loss, and we do the partial derivative with respect to the current weight. So we're only going to want to update one of the weights, not so in other words the weight that's referring to maybe this one or this one. So we only update one weight at a time, and therefore we have to take the derivative of the loss with respect to that weight alone. Now you can work through this yourself. Maybe if you're unsure, ask me a question on the forum. But basically you can see here we've got rid of our 2 on the bottom again because that was squared. The second thing is that we've gone and got the derivative there, and then the derivative with inside of that. And you'll notice that I've got the j written down there in this particular one, and that's because when we get the derivative of x with respect to wj, it'll only be the x part of j, the j part of x that will be important in that particular case. Okay, so that's the reason for that, and that would be basically how we would do our update, and we do our update for each of those weights in order to get the full thing. One problem that we have here is that if we look back at the example that we had problems where features were very different sizes. So if we look at our examples above, they're not at a similar scale. You can see that the mileage could be anything from like 0 to 1 million, whereas the number of doors maybe goes from 1 to 5, and our desirability is only from 0 to 1. What effect would that have on the loss system? So in a very extreme way, you can think of, if we only look at 2 of the features, let's look at the desirability versus the mileage. What you're basically going to have is you're going to have this thing that goes like that. And in fact, even that is not extreme enough. Okay. And so what happens is that if we're trying to descend this landscape here, we're going to head down in that direction. Then we're going to go back the way, and we're going to go down around like that as we go down this, rather than trying to get it and just kind of go down into the center of it here. So it's very much like a valley that we're going to try and find the bottom of, and each side will be very, very steeped because of the particular the particular ones that we're using. Okay, so that's the problem that happens when your features are very different in size. So what can be useful to do is to scale those features so that every feature is roughly the same size. So what should we scale it to? Well, the range -1 to +1 is generally a very good range to use because it works well with our sigmoid function and things like that you're going to see later. So this is a very nice range, but as well, as long as they're within the same magnitude, generally we're fine. So what I mean by magnitude is that, like, it's not, it's not 10 times more and it's not 10 times less. So for example, a feature that went from -3 up to +3, it will do fine alongside a feature that goes from -1 to +1. There's no need for them all to be perfectly matched. And something indeed that goes down as far as maybe -0.3 up to +0.3, again, that would be okay. But if you start to go outside that range, they start to become maybe 10 times one versus the other, and that's generally running into a bit of trouble there. It still it still might work. It should still theoretically work. It just won't optimize very well. So it'll be very slow to get where you're going. So this means that for our car example, we should subtract the mean of each feature from each feature sample. So what we do is we add up all the mileage for all the cars in our data set so that we find out what's the average mileage of a car that we're selling, and we subtract that mean from it. And then what we do is we divide by the maximum value or the standard deviation or something like that, so that we bring it down to being within a value of +1 to -1. So that a -1 to +1 is going to give us an idea of where we are in terms of mileage. Now that of course sounds like we could have a negative mileage, but it's all relative is all it means. So in other words, that this car has lower mileage than the average, and the other car has more mileage than the average car that we would be selling. How do you know if gradient descent is working? Okay, because the other one you can just calculate straight to 0. How do you know if gradient descent is working? So one of the things is that, is it going down after each iteration? So if you're not seeing your loss going down, if doing something along the lines of this over time, if you're not seeing it kind of go down, 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 a little bit more, a little bit more, a little bit more, a little bit more, or whatever, and usually when it levels off, you're fine to stop. If it's not doing that, if it's doing something like this, going up and down and doing that sort of thing, or maybe if it's just going up the way, or maybe staying level, then you know that you've probably got a problem. You're maybe try and change your learning rate, your alpha value or something instead. So it's difficult to tell in advance how long it will take to converge, but you should see it kind of going down constantly. So you can also set up methods to check when it stops kind of getting lower in value, that it's leveled off. Choosing a value for alpha, this can be a little bit difficult, but usually the best idea is to go for something along the lines of 0.001, 0.01, so go up in values of 10, 0.1, or 1.0. Okay, and what you can do if you don't want to quite do that, you can pick values in the middle. By the way, this is a log scale that we're going up in here, so the proper value in the middle would be something like 0.003 rather than 0.005. And if you ever look at log paper, you'll see that that's closer to where the middle would be, and you could do the same with those. So generally what you would do is you might start off with a low value, a very low value, and see that it's descending first of all. If it's not descending at that, you're going to have to go lower again, or there might be something else wrong. But you might see that it's descending, but very, very slowly and taking longer. You can try some of these bigger values then. If you see the loss value going up, that's definitely a problem. Or if it's varying a lot, that's a problem. But if it's still going down and going down pretty fast, then you can start to go up to these higher learning rates and you use them. They're absolutely no problem. As long as it's continuing to go down all the time. You can also, as I say, use situations where you change the learning rate over time. That tends to work better in other systems than necessarily in the linear regression that we're doing, which should continue to drop because of the gradient dropping. So there should be no problem with that. Just to say, where do we go when we go from a linear model? What is the next thing that we do? And the next thing that we would do is where we would basically, for a single variable, we would look at the variable and the variable squared and the variable cubed and so on. So we can then do polynomial, curves and things like that will try and fit data. So that's where we would go next if our data wasn't good enough, and that would have done a reasonable job going back to that guy's example. Where was it? That would have done a reasonable job of trying to do that curve there. If we used some more variables, but it makes the thing more complex and so on. So it's something to keep in mind if you want to look for a more significant model. That's it for tonight, guys. Just obviously some acknowledgements to Scikit-learn, and particularly to Andrew Ng, who's one of the top people in artificial intelligence and machine learning in the world. He's got lots of great videos on YouTube, so make sure to go and watch them as well as my own in order to get a better understanding. Okay, so I'll say goodnight to you at that. If you have any questions, obviously put them up on the forum. Okay.